Hello everybody, welcome back to the course on quantum theory of many-body systems in condensed matter here at the Institute of Physics at the University of São Paulo. My name is Luis Gregorio Dias, and in today's class we're going to continue to look at the second quantization formalism that we started in a previous class. So if you haven't seen or haven't watched the video on the previous class, I'll try to remember to put a link up here. Where there we discussed bosonic and fermionic creation and destruction operators. And today we're going to follow up on that and see how you write one-body and two-body operators in terms of these creation and destruction operators. As an example, towards the end of the class, we're going to introduce the density operator, both in the canonical and grand canonical ensemble. And from that, you will actually derive the Fermi-Dirac and Bose-Einstein distributions for the non-interacting gases for both fermions and bosons. And we can, in fact, write that, this comes naturally from writing the density operator in second quantized form. Okay, so let's go right in. Okay, so let's start talking about one-body operators. So we are very familiar with those from the single particle formalism. So typically when you have an operator, say the kinetic energy or the Hamiltonian, you can always write this operator in a given basis. So you have matrix elements, which for a given basis, the operator might not be diagonal. You have to represent it as a matrix. But you can actually represent the actual operator in the Hilbert space, acting on the single particle Hilbert space, as a sum of these projectors here, which you have here a bra on state var j, phi j, and a cat on state phi k. And as a coefficient, you have the actual matrix element of this guy. So this is an operator that acts on any state in the Hilbert space spanned by this basis. So in other words, this is like rewriting this single particle operator in this basis, right? And of course, you can calculate these matrix elements by, say, doing an integral in the configuration space. You're now projecting these basis states into coordinate spaces, and then you take the matrix elements like this. So it's just a one particle integral. Notice that you only have one coordinate to integrate with. So all particles are in the same system of coordinates. There's only one coordinate system here. So this is a single particle matrix element. Now, if you have, for instance, the kinetic energy, you know how to apply these operators in this basis. It becomes a gradient times, say that this is momentum square in coordinate representation becomes a nabla square. So the Laplacian. So you apply the Laplacian to this state here, and you can calculate these matrix elements. And then you can go back and write the kinetic energy operator in Hilbert space as this. Okay, so we know how to do that. This is single particle quantum mechanics. Now, how about two-body problems or two-body operators? So in the last class, we learned how to construct two particle bases or any particle base for that matter out of single particle orbitals. And we talk about the symmetrization or anti-symmetrization operator, whether you have bosons or fermions. But for short, in this class, I will just represent this as a quote-unquote product state for phi I, phi j. And let's encode the symmetrization or anti-symmetrization in this notation. It means that there will be the net results is that there's going to be a prefactor here to normalize and other different combinations of these guys. But let's just keep that in mind for now. Okay, but this is a two-particle basis, right? So you can, in principle, write any two-body operators as in this two-particle basis. Here again, you have a matrix element, the matrix element between two-particle basis states acting where you can act this two-body operator on them and then take the inner product of this ket and this bra. And by the same token as in the previous slide, you can write this operator in this basis as a sum of these matrix elements and this projector here, a bra capital phi alpha, ket capital phi alpha, and bra capital phi beta. Now, what if you want to write this guy in the single particle basis, not in the two particle basis? Well, then you know what you have to do. You have to write these two guys in terms of single particle orbitals. So each one of these will have two single particle orbitals. So you have a product state for this ket of two kets and a product bra here of two bras for the each one is a single particle states. So yes, you can definitely write a two-body operator in the single particle basis, but now your matrix elements will have four indices, right? Each one of these guys have two single particle indices because each one is a two-particle state, and each one of these guys have another two single particle indices. So you have like a 4-component tensor if you want to write this guy in the single particle basis. Here, this is just the direct product, but of course if you have other terms here in the symmetrization or anti-symmetrization of these, there will be other terms here, like where the indices will change a little bit. So you saw that in the assignment in the second class in this course when you discussed the helium atom. So there you had an anti-symmetrized two-particle basis, and there will be two terms here in the matrix elements. One we call the direct, and the other one's called exchange. Here you might have something like this as well. Whether these will be a plus or minus depends on where you're symmetrizing or anti-symmetrizing. But again, how do you calculate these guys, right? So here, of course, it will be an integral on two coordinates, R1 and R2. So these matrix elements, again, remember, this I and J are the indices coming from this single particle, these two particle basis states, capital phi alpha. So it involves that you have one of the particles in one of the coordinates, R1, and the other particle in the second coordinate. So phi I is in coordinate R1, and the second particle is in coordinate R2. All right. Now this guy will connect both coordinates. So this is by definition a two-particle operator. And then this other state here, phi beta, will have another two single particle states, phi k and phi m. And again, phi k will be on coordinate 1 and phi m on coordinate 2. So this is crucial that you remember that when I look at these indices, I and k are in the same coordinate, and j and m are also in the same coordinate. I and k are in coordinate 1, j and m are in coordinate 2, and I take vr1, r2, and then to calculate the whole thing I need to do this big integral in a 6-dimensional coordinate space. Okay, so just keep in mind here the rule that I and k are in the same coordinate and j and m are in another coordinate. Okay, moving on. Now, what if I have an n-particle basis state? Not only 2, but n. Well, how do I write my one-body operator in this basis? So let's take a look at what I mean by this. So imagine that I have this one-particle operator, right? It acts on particle n of this capital N particle basis. So this guy is acting on this state only, right? Now, how do I represent this in terms of this whole basis? So let's go to the blackboard and take a look on how this works. All right, so let's write our single particle operator in the single particle basis like we did before. So it would be something like that, right? So this is I and j, and there's the single particle basis. Now we have our n particle state, k1, where this k runs from different values of the single particle in this index, k2. Okay, there's going to be a kn for the nth particle up to the capital N k. Oops, sorry. Capital N k. And now I have a single particle operator acting on this particle here, right? The nth particle. Okay, so let's keep writing this. This will only act on this guy, right? So I can even write this something like that, and then this guy will act right here. Only acts on this Hilbert space here. Okay, let's then just write this. Okay, this will be k1 there will be a sum here of I and j, tij, I, j, kn, so in parentheses, and then another products for states, but this guy is only acting here, right? So what do I get at the end of the day? This is going to be, let me change colors here. It's going to be delta j kn, and there's something missing here because jkn, yeah, yes, so no, that's fine. This will stay there. Okay, so let's keep going. K1, when I sum over k, well, I can keep that if you want, but yeah, let's keep it for now. But the sum out here, there's going to be a sum of ij, tij, delta jkn, And here there's another n particle state, k1. Instead of kn, I have I, and then another k capital N, right? You can even, now notice, now I have a sum here. I can even get rid of this sum in J and say something like that. I ti kn times the following. Oh, sorry. K1, K2, etc. At the position N, I'll have an I. This is at position N. Position N. And outside of that, I still have... Okay. So what happened here? Where before I had only one particle state, when I apply this single particle operator into this state, I get now a sum over these any particle states, where the sum runs over only one index, precisely the one at position N, where this guy is acting. All right. So that's how we write the single particle operator in this n particle basis. Okay. So coming back to the slide here, I have precisely this calculation. The sum of the application of each of these guys will produce something like that. Sum of kj, I still kept the delta here, kn, and the particle at position n is this index. And now if I have a sum of these, of n, capital N operators like this will be an operator that acts on an n particle basis, right? And so I carry this sum here, and each one of these will have a sum like that. Notice that I could take out the sum in J and replace J by Kn, and then that would be precisely what we did in the blackboard. Okay, now let's see what we can find if we now consider bosonic systems, right? Where these orbitals come from the creation of particles at a given state K in the vacuum. And of course the bra will be the complex conjugate of that, right? So the one body operator that we had these matrix elements. So I had the two body operators here and here. I'm not going to you can think that I have to get the symmetrized version as well of this, right? So there's going to be another term here, but let's forget about that for a while, or if you want, you can implicitly say that you have more than one of these terms considered here. But in the anybody space, the anybody Hilbert space, the operators that will be acting there are precisely these: the sum of 1 to capital N of single particle operators, or the sum of these guys, two particle operators, not restricting the sum in n and n prime, and then you have to add this factor of 2. We discussed that on the other class where we talked about these two body operators. Or you could just restrict the sum to n larger than n prime, and then you wouldn't have the 1/2 here. But let's see. So these in any case, these two operators, they act on the anybody Hilbert space. Okay. All right, so how do we write, or how do we apply these n-particle operators onto number occupation states which live in the same Hilbert space of n particles, capital N particles? Now, first thing to remember is that when you write these number occupation states, what we are actually doing is representing a state where we start from the vacuum and we start creating these bosonic particles. So we apply n, capital N, times the creation operator for state n, or nk times the creation operator for state k, for a bosonic particle in state k, and so on and so forth, right? And by applying that, aside for normalization factors, which you will calculate later, right? So there's be square roots of n here somewhere, but you get to this normalized state at the end of the day. So, right? So this is actually what it means to apply this guy. Now we're going to show that if you apply the sum of single particle operators into this guy, what you get is this: the matrix elements Tkj times b dagger k bj apply to this one. So let's see how does that work in the blackboard. Okay, so let's start with the result that we had before, that when we apply this operator into this state, I get this, remember? And I'm actually not going to make or to provide a very rigorous proof of this statement before. Remember, what we want to show is something along these lines, that this can be written as this: Tij b I bj. All right, so I'm gonna do an example, and I believe you can generalize from that example. So let's start with a basis of 4 elements. Okay. And let's start with a 4-particle state like this. And 1 equals 1, and 0 equals 1, and 1 equals 1, and 2 equals 1, and 3 equals 1. So that means that this equation would be something like that. So who's this state? Well, it will be something like this: 0, 1, 2, and 3. Okay, you could have other occupations. So this is an n equals 4 state, right? So what does this equation tells me in this case? It tells me that I have T thought applied to phi0, phi1, phi2, phi3, that's my left hand side, equals a sum over n equals 1 to 4, sum over I and j spanning this basis, also going from 1 to 4, Dij delta j kn, or where this kn is also an index going from 1 to 4, of phi k1, phi k2, etc., except the position n, I get phi I. So let's write this sum explicitly. So of course I'll have 4 terms here, and I'll have this sum over ij out here, Tij. So n equals 1, I get j k, the first one is 0, so 0, and I get right at position n. Remember, this is a position n. I get this. Position n is the very first one. I get phi I. And then I get the other ones, right? Phi k2. K2 is 1. 1. So this is I. So yeah, let's make it another color. So that we keep track of what the I is. All right, this is 1, 2, and 3. Should be 3. There's gonna be another one, J1, phi 0. Now my phi I will come here. Phi I plus delta J2, that's position 2, right? Phi 0, phi 1, phi I, I'll put the I later, J3, phi 0, phi 1, phi 2, and a phi I here. Let's put all these two I's here. They're missing. All right, let's go. All right. Oops, sorry. Yeah, let me erase this. Something that was left over from a previous calculation. Okay, so let's now notice there's a sum in I here, so I cannot do that, but I know how to write these guys in terms of occupation operators, right? I'm just getting this a creation operator of I here and the other ones. So this guy, what is this? This is T thought B dagger 0, B dagger 1, B dagger 2, B dagger 3 over at applied at the vacuum, right? Now I have these B dagger I here. Now what I'm going to do is simply this. So I'm replacing, say, B dagger 0 here with a B dagger I. So what I'm going to do is this. I'm going to use that B I dagger B, say, K, KN, or let's like this. B dagger I apply to the vacuum is actually the same as applying B dagger I and then B dagger KN, B dagger KN to the vacuum. That's what I'm gonna do. Okay, so essentially I'm going to replace all this with a B dagger I, B dagger K, and in order to get back the same state here on the left hand side. So let's see how that works. So here is some ij, Tij. I'll have the sum here, delta J0 Now I had a B dagger I. I'm going to replace that with a B dagger I, B dagger Kn. Kn here is the first one, which is 0, B0. Then J1. Now it's going to be a B dagger I, B dagger I, B dagger. Position 2, I got 1 plus J2, B dagger I, B2 plus delta J3, B1, dagger 1, B dagger 3, and that is multiplying the same state as before, as on the left right hand. 0, 1, 2, and 3 apply to. So this thing equals to T dot. And you can just check that this is simply Ij, right? There's this delta J here, but J goes from 0 to 3. So this is simply, right? This is, you can replace that by J, the 0 by J, since you have the sum on those, Bi dagger Bj, okay? Okay, so that essentially makes our so this T dot B0 dagger B1 B2 B3, oops, B3 equals that. So you can infer that this is actually T dot. Okay. Now in the book and then in the notes there's a more rigorous proof. Here it was very simple. I mean, I just showed for this state, but in principle it works as in general as a operator identity. Okay. So we argue that this works, that you can write the operator, the sum of single particle operator in terms of these B dagger and B operators. Now you might want to show, and that's in the assignment, that the same can be done for the interacting part, for the two particle operators. And here is going to be even more interesting, because now we will get the structure of 4 operators, and that's very characteristic of interactions. Now notice this order here, K and M and K. For bosons it doesn't matter much, but for fermions it does. But this is the order that it should appear typically. Remember that I and J corresponds to particles in the same coordinate, and K and M on different coordinates, right? So this is how you write the two particle operators in this number occupation basis. And then we can write the sum of single particle operators and the sum of two particle operators in terms of bosonic operators, like this, in this basis, right? TKJ, these are the matrix elements, and written in this basis for the orbitals. This we already covered. And it turns out, and this is quite remarkable actually, that for fermions they take the same form, even though the way to prove is slightly different, because now the occupation numbers can be only 0 and 1. But you can show, and that's also in the assignment for you to show that and get more familiar with this notation. because from now on we're going to use it very, very heavily. Turns out they have the same form, right? And in fact, we can even have a pictorial view of how these operators can be represented in terms of diagrams. Now, they're not really Feynman diagrams at this point, but there's a lot of resemblance. We can make a very interesting connection. So here you might view this as like a scattering picture. Okay, it means that when you write it something like that, you are destroying a state J, creating a particle in state K. It's like you were scattering, if you want, quote unquote scattering from state J to state K via some sort of one particle operator, right? So you come with on state J, this gets destroyed, you create a state in K, and here is the interaction is given by this matrix elements, this kind of scattering term, right? It's not exactly scattering, of course, works like that, but this is much more general. This is a one body term, right? So for the interacting parts, the thing is a little bit more subtle. Remember that when you calculate these integrals, I and K are in the same position, and J and M are also in the same position, R1 and R2. Now you are creating states in I and J at different positions, so you are creating these states, and you're destroying K and M, or K and M also in different positions, K and M, right? So it's like these two particles, and this is kind of happening quote unquote at the same time. So this represents really a two-body interaction. So K and M are being scattered, but they also interact with each other at two different positions in space. So this is a pictorial view of what these and these represent in terms of these single particle orbitals. Okay? So we'll come back to that and be more rigorous on what these things represent and so on. Now, let's give an example, very important one. Especially if you're talking about non-interacting Hamiltonians. For instance, a Hamiltonian which is a sum of single particle Hamiltonians like that. How do we write this many-body, this n-body term in terms of creation and destruction operators? And what we do is essentially what we did before. Let's go to the blackboard and see how it works. So again, we show that the single particle operators, they can be written in terms of either bosonic or fermionic operators as this, right? Ij, Dij, I, and J. Now our Hamiltonian, and this is an operator that lives in the n particle Hilbert space. So our again, T tot is a sum of these single particle operators. So our Hamiltonian in the non-interacting case is also a sum of non-interacting or single particle operators n, right? So it means that if I write in this basis where Hi equals an energy I, these are eigenstates of these single particle operators, I would get something like that. I and J, H, I and J, let's see for bosons, for instance, this would be Bi, Bj. And sorry, here I wrote what we proved, or we didn't exactly prove, but I gave you the most arguments favoring this property of the operator. So, but this guy is diagonal. This is hi delta ij, right? Because it is diagonal in the spaces. So this is essentially I h. Oh well, who's the? This is the energy. So this is EI, BI, BI. All right. So this is single particle. This is a single particle Hamiltonian in n-body form. Either in bosons, for bosons, or for fermions as well, is the same. Okay. All right. So coming back to the slide, from that we can of course get the many-body spectrum, because this is the number operator. So if I apply that into this state, what I get is for each k, which is k is an index of the orbitals, I get a different number with a given energy. So this is actually a number. These are real numbers and these are integers. So for what it tells me is that a state in the number occupation representation is an eigenstate of the Hamiltonian, right? Which is natural to be, right? And then the energy for this state is just the sum over the single particle energies times the occupation for that orbital, and this is quite useful, because then I have the many-body spectrum already if I know the single particle one, right? So I can just fill up the levels, as they say, either with fermions or either with bosons, and that's how we create these many-body states. And of course, this has a very nice application in statistical mechanics, where you can study systems of many particles as long as they are single particle states, or the Hamiltonians are not interacting. It's just a sum of single one-body terms, even for very large numbers, the spectrum. And that's what we're going to address next. Let's introduce this very important operator, which is the density operator, either in the canonical form or in the grand canonical form. So what is this? So imagine that you have your system described by this Hamiltonian with n particles, and let's consider that n is fixed. So you have a well-defined number of particles, and then you couple the system to a thermal reservoir at a temperature T, and this will give you the thermal response, if you want, meaning that this operator essentially is the exponential of minus beta, the inverse of the temperature, times the Hamiltonian in the exponent. So, okay, what does the exponent of an operator means? Well, this is just a representation for a series in powers of this h dot that will recover the exponential. So you know how to apply that into any state in this Hilbert space, in this n-particle Hilbert space. Now, the grand canonical one is when not only you exchange energy with the reservoir, but you also exchange particles. So now you get a temperature and a chemical potential that describe your thermal state. Now, if you have the many particle spectrum, it turns out that you can calculate the partition function, with the Boltzmann weights, and this is the many body energy for a given configuration, for a given state, and this will simply be the trace of the canonical or grand canonical. So here is the canonical partition function, but you can calculate the grand canonical one by taking the trace of this guy. It's just a trace of the density operator. And notice that the trace is invariant and under which basis you take. So here we choose to make the trace by summing over the eigenstates here. So where I can calculate this matrix elements very easily. So that's what we get the partition function, right? With the Boltzmann terms and so on. Now the thermal average for a given operator is also nicely given in terms of the density operator, as it is essentially the value of the operator, the expected value in this basis, which defines the eigenstates of the n-body Hamiltonian, times the Boltzmann factor with a given energy for this state. So you add this and divide over the canonical partition function, you get the thermal average in this ensemble, the canonical ensemble. Of course, if you want to go to the grand canonical one, you have to replace the density operator by the grand canonical density operator here. And that's precisely what you're going to do. And notice that here in the canonical one, the number of particles is fixed, but in the grand canonical one, the chemical potential is fixed. So that's essentially what we're going to do, or you are going to do in the assignment. Given the non-interacting Hamiltonian, you're going to calculate the thermal average of a very special operator, which is the occupation operator for a state K. All right. So this is how you're going to calculate. You know how to formulate the basis in these states, right? And you're going to calculate that for both bosons and fermions as a function, say, of the energy, right? Because K is a single particle state, so you can calculate this as a function of single particle states, for instance, and see how does that work for bosons and for fermions. Of course, the chemical potential will enter here. So this is the typical calculation that we can do if we know the spectrum. If you know the spectrum of a given system, we have everything, right? We have the partition function. We can calculate any thermal expectation value for that. Now, in general, if I have interactions, then things are more complicated, and that's the whole point of this course, to see how we can at least have approximations from things like that when we don't know how to calculate this trace, when the Hamiltonian is not like that but has an extra term here. All right, but for now, let's play with the non-interacting case and see what you get out of here. All right, okay, have fun, and I'll see you next class.